here. So now Leandro will have 50 minutes to present his PhD thesis work.
Let me just try to share my screen. Right. Sorry. Okay. Can you see my my cursor, or in case I need it? Okay. Well, I couldn't hear you. I assume that it's fine.
Yes, you can.
Yes. We were thumbing up.
Okay. So. So thank you, everyone, for participating on the thesis, especially to the members of the committee. I'm very happy with the committee that I gathered. In particular, thanks to Milton and to Wioletta for the last 4 years. This thesis is really a set of 3 projects that go in slightly different directions. They are not connected in a single thread, but they are all examples of long-range diffusions, and we really use green functions to study all of them in different ways. But so before I set up each of those parts, well, those are the 3 articles that we're using for this thesis. The first 2 are with Milton and Wioletta, and the last one is with Claudio. So I will just set some notation before I start. D is going to be our space dimension. Actually, in part 1 and 3, this dimension is going to be equal to 1, but in part 2, it's any dimension. We will take the torus to be with side length 2 pi, and this choice, it's just because we're using characteristic functions in part 1, so it's nice to really be the inverse Fourier transform. So this is what carries some pi factors throughout the article, throughout this thesis that are not in the original articles. We also will want to talk about a discrete torus. We'll be talking about scaling limits at some point. So we have ZN, this discrete torus with periodic boundary conditions, and we have a normalized version of the discrete torus. So the first part of this that is not completely, I mean, it's a very famous operator, but it's less famous than the standard Laplacian, is the fractional Laplacian. Here we have a parameter alpha between 0 and 2, and for any function with at least 2 derivatives and that is bounded, we can define the fractional Laplacian of a function in terms of, well, it's a constant times the principal value of this integral. And for those who are not familiar with principal value, it doesn't really matter. You can just think of the integral itself. And how it works, it's in some sense a generalization of the Laplacian. The Laplacian, you're at any point for given f, the Laplacian of f at a point, it's basically comparing the values of f against its infinitesimal neighbors of the point x, right? So here there is the same idea of making an average of the differences, but instead of just being across the these infinitesimal neighbors, it's really across the whole RD. So some properties that are important for such operators are, first, this is non-local, in the sense that if we have 2 functions that they have the same values within a certain domain, they don't necessarily share the same fractional Laplacian. The second part is that this really interpolates between the identity and the usual Laplacian. That is, if I fix f with 2 derivatives, bounded derivatives, and I fix x as well, if I take the limit of alpha going to 0, we recover the identity, and taking the limit of alpha going to 2, I recover the identity. Oh, sorry, the Laplacian. This for fixed x. Right. It has a nice Fourier transform. The Laplacian itself has nice properties with the Fourier transform, and this really translates into nice property, like spectral properties. So this is how you can approach the fractional Laplacian. There are several definitions of fractional Laplacian, one of them being the spectral version. And finally, I'm not going to spend a lot of time on this now, but basically alpha dictates the regularity of the operator. So if we're solving an equation with fractional Laplacian, that somehow you would expect to gain alpha regularity. We will visit this again throughout the thesis, so I'm not going to spend more time on this right now. We also want to, and sorry, one thing that is important to mention, we chose alpha between 0 and 2 here, just so this even in principal value for this integral to converge. For alpha bigger than 2, this doesn't converge anymore. But we can define a fractional Laplacian even on the discrete setting, so in ZZ. And it's the same idea again. We're averaging the differences between f at a point and its any other point against a kernel P alpha, which is going to play a significant role in this whole thesis. But it's nothing but a probability distribution that is a power law. That's decaying according to a power law. And here, because we don't need to worry about problems of convergence, we can define alpha to be any positive number. Okay. As I mentioned before, we'll also be interested in periodic settings. So I want to transfer the fractional Laplacian to the periodic case. To do this in the continuous fashion, well, this is easy. The fractional Laplacian was defined in any function C2 with bounded derivatives in RD. You can just extend the functions in the torus periodically and compute the fractional Laplacian there. For the discrete case, it's slightly more intricate, but it's not particularly so. We have to think of this discrete fractional Laplacian that we presented before, periodic extension on ZDN for a fixed parameter n, and there is a certain mapping of renormalizing ZDN to TDN. Okay, so these were all my notation, and so we start the first part of this thesis, which is about central limit theorems, in particular local central limit theorems, heat kernel estimates for heavy-tailed random walks. And the question that guides this, it's a somewhat naive and ill-posed question of what is the best random walk in the domain of attraction of a stable distribution. When you're talking about, say, easy model, or if you're talking about some random walk approaching, if you want to work with a local model, so say you're trying to work with a model that is somehow approaching the Brownian motion, well, if you want to simulate this, most likely you're going to use a nearest neighbor random walk. If you want to work with an easy model or some IDLA model, and you want the diffusion to like the scaling limit somehow to have a relationship with the Laplacian, you're likely to choose the nearest neighbor interaction as well, just because it's the simplest one. But there is no clear definition of what is the simplest one in the case of stable distributions, because you can't have a random walk in the domain of attraction of a stable distribution with bounded domain to start with. You need to have a heavy-tailed random walk. So we'll start by thinking of a random walk, and now I'm going to restrict alpha between 0 and 2, but I will think about the random walk according to which the steps are taken according to P alpha, that power law that we worked before. And it's this random walk, properly renormalized, it converges to a stable distribution, which even though if we can't describe it pointwise in a nice fashion, the density of such stable distribution, we can still describe it in terms of its Fourier transform or its characteristic function. It converges to this nice distribution for some parameter kappa alpha, which can be computed as well. And what we want to study here, why I'm talking about local central limit theorems, it's usually in terms of the density, trying to control the density. We want to estimate the difference of densities between the random walk for which steps are sampled according to P alpha, and the random walk whose steps are sampled according to P x bar. And we want a uniform bound in this, and we want to understand how this decays according to K. So first, I'm going to compare such results to the normal case. So suppose that's your random walk. I'm going to assume symmetry here, just for convenience, but it's not mandatory at all. So suppose that you have a random walk, which is symmetric, and you can then do a similar kind of result comparing to the stable distribution, symmetric random walk with at least two having at least two finite moments. The stable distribution associated to it is going to be some normal distribution with a given covariance matrix. And So sigma for us is this given covariance matrix. And one can prove that this is going to converge at least with this speed of convergence, that decays as a power of k. If you don't assume anything extra, so you just assume that your symmetric random walk has two finite moments, Gnadinko's local CLT, which is a very classical result, shows you that beta is equal to 0. That this is at least, you can at least get this result with beta equal to 0. But there is this this book by Lawler and Limick in which they do more general results, and in particular they assume either that the steps of your random walk have 3 or 4 finite moments, and assuming that they can improve the rate of convergence of the random walk. Moreover, these betas are optimal in the sense that only given those assumptions, you really you can't get anything better, any better beta for those class of random walks. So how do we do this in the context of stable distributions, right? Because the heuristics that I'm going to call H here is basically, well, if I assume further moments in the step distribution of my random walk, I then have a better rate of convergence. But how do I translate this to the case of heavy-tailed random walks? Because basically, when I think about if I think about random walks with 2 finite moments, if I now consider random walks with 3 finite moments each step, this is still in the domain of attraction of a normal distribution, right? But if I'm studying for alpha is smaller than 2, and I assume a further moment estimate, I'm leaving the domain of attraction of the heavy-tailed, of the same alpha stable distribution. So I cannot do this. So this is not the right heuristics for our case. So before I talk about how we solve this, just a few results in the area. Again, Gnadinko's local central limit theorem shows that you can get a bound that is at least of order k to the -1 over alpha, without any further assumptions. More recently, there's those results by Caravenna and Done, which they do upper bounds for the density, so not the difference. So instead of looking at this difference here, they are looking at the density, not comparing to the stable distribution at the end, but just the density itself. And they do for the case alpha different than 1, but they also study properties of strong renewal here and there. They excluded the case alpha equals to 1, but Berger also worked in the same year. They published results similar to the ones above, and also some non-symmetric for when the random walk is not symmetric, getting some estimates for the green functions. And finally, just mentioning that there's there are results in other metrics, say Komogorov, Mallow's distance, Zolotarev distance. So there are central limit theorems according to other norms as well. But to the best of our knowledge, the best results that were known before this article were really of the order of Gnadinko's local central limit theorem. Right. So turns out that if you visit Lawler and Lemick's proof, moments that they assume were nothing but a convenient way of understanding the characteristic function. Say, if you assume that you have m finite moments, you have the characterization of the characteristic function up to order theta to the m, around theta equal to 0, right? This is the first course of probability theory. So, but this comes from Taylor expansion. And what happens in our case is that Taylor expansion is not particularly good because when alpha is fractional, if alpha is between 0 and 2, you're not going to have any derivatives after order alpha. So so trying to understand the asymptotics of your distribution in terms of derivatives or in terms of the moment ceases to be good. But you can still do this by hand. And this is precisely what we did. In the case of one dimension, we studied the characteristic function for our distribution P alpha, so that power law, for any alpha between 0 and 2. And we obtain the coefficients explicitly. Kappa 2 does depend on alpha, but it's positive. It's actually a infinite series, which is a bit annoying, but you can show that it's positive. And this is going to be important in a bit, actually. And this is one of the points that it's kind of tricky to do for any dimension. We do expect the results to hold for further dimensions, but there is no clear way of obtaining this characteristic expansion for any dimension. We believe we can do dimension 2 or 3, but it's tricky for high dimensions bigger than that, because we depend on some numerical computations as well. And the idea here is that the presence of those constants, so kappa 2, it's almost like a cumulant. Cumulants are one of many ways of understanding the Gaussianity of a distribution. This is used in probability often. And basically, we're allowing for powers that are not just integer, but can be any fractional cumulant instead of just integer powers. And it's going to be, it turns out that we can reframe the what Lawler and Limmick use. Instead of asking for further moments, it turns out that what is actually useful for us is to have that the error after this term, kappa alpha, is small. This is going to give us the rate of convergence of the random walk. And again, this does come down to the idea of cumulants. Right. So if we know that kappa 2 is positive, we can actually generate a random walk whose law, on ZD, whose law is whose characteristic function is given by this. This is easy to do. You can just get a random walk which obtains 3 values, 0 plus m and minus m, and m's are given according to kappa 2. So it turns out that now, remember, what we're trying to do is not necessarily think about p alpha, but instead we're trying to get a good distribution in the domain of attraction of the stable distribution that we're working with. So it turns out that if we take one step according to p alpha and then one step according to pz, we have a characteristic function that is much better in terms of the error term after kappa alpha is of much smaller order. Instead of being 2, it's 2 plus alpha. Right. And this idea is kind of repairing the distribution, which is somewhat reminiscent from a paper from Frametta and Jara. They used in a different way. There it wasn't really summing distributions. It wasn't a convolution of distributions. They used a convex sum of 2 distributions, but the idea is kind of the same. And what is nice then is that we can now recover a rate of convergence. This is in dimension 1. This result holds identically in any dimension, but it's just that we don't know the characteristic function of p alpha, for instance. So this repair distribution converges really fast to the stable distribution of our interest. And right, this is good. And this is actually as good as in the normal case. If you substitute alpha by 2, you actually recover what you would have in terms of the simple random walk, for instance. So you're really getting something somehow that is converging as fast as the simple random walk converges to the normal distribution. So this is good for us. But it turns out that this, back in Lawler and Limmick, they also had a non-uniform bound that improves as x goes to infinity, and we cannot recover that. This boils down to the fact that the fractional Laplacian, the continuous fractional Laplacian, doesn't have a good product rule, only an approximate one. And that kind of breaks the proof that they used there. So, and this proof was used to get good estimates on heat kernels and green functions. So we have to use a different approach. We go through Fourier analysis again. They kind of abandoned Fourier analysis at this point. We keep going with Fourier analysis. And we can then prove that here I'm only stating for alpha between 1 and 2. In the thesis is also for alpha equal to 1. You've recovered the first term is a logarithmic term. And we can actually prove up to alpha equals to 2/3, and then it's not the heat kernel anymore, it's really the green function. And what is nice here is that we characterize up to like a vanishing term. Before this paper, the best results that I know were about the leading order term. So we're really improving in this sense. Unfortunately, this proof kind of breaks down as as the dimensions grow, because basically we're not really able to improve this power here, but for dimension 2, the leading term is already going to be smaller than this. So we need to, our proof is based on trying to show that an error is smooth enough. And this is, so the Fourier transform, the Fourier series of something that is very smooth decays with a certain speed, and that's our approach. So we either, for higher dimensions, would expect that we would need to somehow expand the characteristic function even further to be able to apply the same techniques. But you might have noticed that we haven't used at all the density of the distribution itself. We really used the characteristic function at the end of the day. So we can extend all of our results, not just for the P alpha that we just talked about, but for any random walk for which we can compute the characteristic function, which is a nice class. It's closed under convex sums, it's closed under convolutions. So we call distribution which is symmetric on ZD admissible if we can expand the characteristic function of it. And again, this kind of rely on this idea of cumulants. Right, and we only have to track up to order 2 plus alpha. After that, that's not really useful for local central limit purposes anymore, but it might be useful to get better rates of convergence, better error terms in the green function. And also, so we recover all those results, and we can even show that our results here, we really need to repair the random walk if we want these speeds of convergence. We can actually show that if we don't have such a nice and clean repair distribution, the rates of convergence are worse, and the error term here is actually worse as well. Okay, so for the second part of the talk, I'll be talking about long-range sand piles and fractional Gaussian fields, but I will actually skip long-range sand piles almost altogether just for sake of time, and I'm going to go straight into the field that is related to them. But just in a few words, sand piles for us, so we're talking about the divisible sand pile, is a diffusion process. In our case, is going to be long range as well, and it's a mass distribution. But it's basically, it only transports mass if you're above a certain threshold. Such fields are related to, they give rise to fields called odometer fields. And it turns out that those odometers, up to a random shift that I'm not going to enter in detail, solve this equation that we're looking at right now. So just keep through and go straight at Hn, which for us is going to be the solution of this discrete equation in the normalized torus. So it solves the Poisson equation, for which the potential is a noise. And because we're in the torus, we ask for the average to be equal to 0. Notice that we're not assuming at this point that the noise is normal. We're only assuming finite second moment, and we're assuming mean 0 and variance 1 just for convenience, but this is not important at all. And what we're going to do next is to study some supremums of like the supremum of Hn as n goes to infinity and scaling limits of those fields. So just a few images to illustrate this. This is in the case of sigma actually being normal distributions. And you can see it's kind of reminiscent from that idea that I gave before, is that as alpha grows, the solution of solutions of Poisson equations with fractional Laplacians grow in regularity. So it turns out as alpha goes to 0, the solution Hn will basically become independent from each other, and we keep gaining regularity up to the point that we get to alpha equals to 2. You would think that maybe if I put alpha equals to 17, this would be even more regular. Turns out that this is not the case. And the idea here is that the moment that alpha is bigger than 2, you have 2 finite moments. You are in the domain of attraction of a normal distribution. So you actually are not going to have any regularity better than the Laplacian itself, which is the than the Poisson equation with the actual Laplacian. So results themselves, we just published. Is the first one is in the case of actually sigmas are normally distributed, but IID, and we can characterize the average of its maximum. There is a whole study of maximums of normal fields, and so here this is just a part of our results, is to understand this expected behavior. And notice that, again, as I was just mentioning, if alpha goes beyond 2, you don't actually have any big difference in behavior. It's the average behavior really depends only on this parameter gamma, that is the minimum between alpha and 2. Right? It will change the constants, but not really the speed of convergence. And this extends the results from Levine, Muburkan, Perez, and Urkan, for which they did similar results, but really with the simple random walk. In that case, they were talking about the normal discrete Laplacian, graph Laplacian in TDN. And it's nice because so we recover their case, their speed of convergence, if gamma is equal to 2. And this is nice because it just makes us think that this doesn't depend even on the P alpha, on the precise form that we're taking P alpha here to be what guides the fractional Laplacian. It could be any such distribution, any distribution in the domain of attraction of a stable distribution as well. Right. The second part of this paper regards scaling limits of such fields, which we are basically defined as fields that are locally constant around each point of TDN, and we rescale according to this. Again, notice that the main factor here is gamma, and not necessarily alpha. The only place where alpha shows up is if it only matters in case its alpha is equal to 2. This is because I actually avoided, we didn't do the result here for alpha equals to 2. The power law case with alpha equals to 2, you're not in the domain of attraction of a normal distribution because you don't have finite second moment, but you're also not in the domain of attraction of any other distribution. You depend on some further log corrections that here would depend a lot on the dimension, but in this case it's simple to write. And we can show that this converges to the Gaussian field, the fractional Gaussian field of parameter gamma. Few examples of such fields is for alpha equals to 0, this is the white noise. For alpha equals to 1, this is the GFF, it's very famous. And for alpha equals to 2 is the Laplacian, which is a bit less famous, but still very important field in probability. So it's nice that we recover basically the whole story according to alpha. When alpha is bigger than 2, we really recover the local scenario. Just a review of results before us. Cipriani, Rasra, and Ruszel have done the original paper in this area, I would say, it was by them, and it was in the case of IID noise, so sigma IID, but each of them having finite variance, and all of the results that I'm going to present here, it's really for local interaction, so the standard Laplacian. In the same year, they also considered the case in which the noise has heavy tail, and this converges instead of the Laplacian that you would recover in the previous paper, it converges to some form of fractional field, so stable field, which generalize stable distributions, basically. And finally, there is this paper by Cipriani, Erhard, and Ruszel, that they studied the case of Gaussian noise, but with covariance. And there they recover fields that are smoother than our case. So you manage to recover smoother fields as long as you introduce some covariance of correct form. Okay. Right. And okay, so finally, I'm going to go to the third part of the talk, which is also the one that I'm going to put the most amount of things under the carpet, because it's a bit trickier. But what is the object that we're going to be studying is this SPD. So it's basically the heat equation for the fractional Laplacian, actually for the half Laplacian, so we're being very specific here, and with a nonlinearity of hyperbolic sign, kind of nonlinearity. And we have this last parameter here. She is the white noise. So what is important when you first look at these equations is even to what does it mean? Because you don't expect the solution for such equations to be a function. You only expect to be a distribution. But there is no clear way of multiplying two distributions. So there is no clear way of squaring a distribution, much less understanding what is the hyperbolic sign of a distribution. So you need to be more careful here to make sense of all of this. Right. So before I start talking about how we give sense to this equation and proceed with our results, I will just give a very, very oversimplified version of the history of such PDs, starting from already jumping quite far, is thinking of about SPDs that were studied in the Prato de Bush paper in 2003, and they introduced this the Prato de Bush trick that we're actually going to use here as well. And they looked at polynomial nonlinearities. There, I think they allowed for all the kinds of noises besides the white noise, and they allow for small degrees depending on the regularity of the noise. Here I'm skipping a lot again and going straight to Harer's, Martin Harer article on a theory of SPDs that gave a more systematic study of regularity structures, and here I really skipped a lot of things. For our purposes, until this point, most SPDs that I know of that have been given good mathematical context had like a polynomial kind of nonlinearity, even if it was a polynomial on the derivative or something of the sort. So in Harer-Shan and later on Shander Harer-Shan, they study a sign kind of nonlinearity. After that, Garbin also studied exponential nonlinearity. And all of those papers were really done with ideas of using the standard Laplacian, so it was really local kind of results. The first paper that I'm aware of during this kind of results for known local operators was done by Ignat and Otto, but in their case, they're not working with an initial value problem, but instead with something that is periodic in time, so they can take a bit of advantage of the fact that you can do Fourier analysis in time as well. Right. Just would like to really point out that there were a lot of other results in SPDs, even from many members of this committee, that came from rough path, from regularity structures, from approaching by particle systems, maybe energy solutions and things like that. And also for other equations that I didn't even talk about here, such as KPZ equation, the 5,4D kind of equations. So this is really an oversimplified history. So, okay, now I'm going to give a draft of what we're going to do. So if our equation didn't make sense at first, maybe the first thing that we should do is to somehow regularize the equation, maybe modify the noise against some modifier. This makes all the terms in the equation to be functions, so we can actually solve the equation, at least for epsilon positive. Next, we split such solution that we obtained in step 1 in between a regular part, but it's very explicit, and a more regular part, but that is less explicit. I will talk about it in a second. And by doing that, we discovered that the whole problem of making sense of the solutions as epsilon goes to 0 is because the equation given for W epsilon bar has some terms that explode, so you need to renormalize it. And this might look non-intuitive for people who are not familiar with SPDs, but this is very much in the same spirit of when we renormalize the central limit theorem, we need to take the average out of the equation, right? We need to subtract n times the the main value. So we're really subtracting something that is infinity. So we need to somehow renormalize whatever object that we're expecting to converge before recovering some form of convergence. Now we look at this new, we're going to somehow change the equation for W epsilon bar to get a new equation for which the solution we're going to denote by W bar, W epsilon. And this equation for W epsilon can be phrased in a fixed point kind of argument in a nicer setting that we can actually prove that everything converges, that this fixed point is actually maps, the operator in this fixed point actually maps a certain space into itself, and it has nice continuity properties. Okay, so, and then we can finally actually define what we mean by the solution of such kind of equation by being not this U epsilon that we defined before, but the U epsilon, but with the renormalized solution. So it's basically at the beginning of this whole game, we're looking at the wrong equation. We needed to have renormalized the equation to start with. And this, again, might seem a bit alien. It might feel like you're just changing, moving the posts as you go along. But it's this kind of renormalization and looking at other equations, it's actually the physically meaningful solution to such equations. So before I keep going with this result, with our results, I just would like to give a word on the kind of spaces that we're working with. Those are the so-called Bezold spaces. They are also referred as negative Holder spaces or Holder spaces of negative regularity. And why introduce those? The idea is basically, well, when you're studying the Brownian motion on your first course of stochastic processes, one of the first things that you see is that it has some scale invariance. If you zoom in around certain point of the Brownian motion, this thing actually, and then you multiply. Yeah. So basically, if you have this scale invariance kind of principle, and the fact that we obtain this this power here, this exponent half, is no coincidence with the fact that the Brownian motion, each path of the Brownian motion is almost surely Holder up to order half minus, right? You actually use this in the proof and for the continuity. And the theorem that connects this self-similarity with actual continuity properties is the Kolmogorov-Chentov continuity theorem. So Bezold spaces are basically the spaces for which we can really take advantage of self-similarity. But because we'll be working with distributions, you don't have something that you're going to have negative powers instead of positive ones. Basically, you understand the rate of explosion around each point instead of the rate of convergence around each point. So this is the kind of space that we'll be working with. So let's apply our steps. Step 1, we regularize the noise, and that's our original equation. And so we just regularize noise, denote the solution of such equation by U epsilon. Okay. Second step, in terms of those spaces that we're just talking about, it turns out that we can split U in the sum of two parts. One of them is this V epsilon that solves this equation, and there is this term here that I'm going to be ignoring. For those who understand, it's basically the price that we're paying for. We're slightly changing the semigroup of the half Laplacian for integrability purposes, but it's basically the linear equation, and don't worry about it. And then you have this epsilon bar. Oh, sorry. You have this W bar epsilon, and this is this should live in a battery space. Basically, if we now look at the equation for W bar epsilon, the solution is this. Oh, sorry. The equation is this one. Notice that because I put the convoluted noise or the regularized noise in the account of V, it cancels out when we look at the equation for W. So it turns out that none of the terms here are as irregular as this one. So we expect W epsilon to be more regular than V epsilon. But the thing is, V epsilon is, it might be irregular, but it's very explicit. You can just understand it in terms of heat kernels, semigroups, very explicitly. It's just a convolution against something. Whereas W epsilon is not as clear what happens to it. And it turns out that, as I was saying, what really doesn't let this equation, this U epsilon, converge to anything meaningful without renormalization is the fact that are those terms here, those exponentials of V epsilon. It turns out that they don't converge to anything meaningful if you don't renormalize them. And so we can actually renormalize them. And so we're recentering this field. And for those who have done a course in martingale theory, it basically, when you're thinking of the exponential martingale, so if you think of the exponential of the Brownian motion, this is not a martingale anymore. So you really need to take the variance squared. You need to take the variance divided by 2 in the exponents to make this thing to be a martingale. And it's kind of the same idea here again. It's basically by introducing this term, this renormalization term, the average behavior of this exponential keeps leveled at 1. And we then have this new field, x gamma epsilon, and this field actually converges to something meaningful. It converges as long as gamma is sufficiently small. We actually can prove that this is converging to a final field, C alpha, x gamma in some Bezoff space, where we actually understand what is the maximum value for alpha. Okay, so we already have, we now know what is the new equation that we need to work with. I just would like to mention, I'm not really talking about it here, but this really uses Gaussian multiplicative chaos theory. You can just see that V epsilon is a log, has a log type covariance, so you can make sense from Gaussian multiplicative chaos. Okay, so now we have this new renormalized equation. Again, I would just keep this term under the brackets. And this equation actually has a nice, it has chance to actually converge to something, the solution of this equation. We can rephrase this equation in terms of a fixed point kind of argument. So the solution of this equation should be the fixed point for this operator here. And the operator is constituted of the following. First, we exponentiate whatever is the field that we're working with. So we need this field to be actually a function for this to even make sense. Then we multiply by this x gamma epsilon. So we'll multiply by something that is essentially a distribution, or that is converging to a distribution. Then we convolve with our modified version of the of the semigroup, or of the semigroup of the half Laplacian. We do the same for the negative powers. It doesn't change anything. And then there is those two bracket terms. One is from the one that I was already not talking about, and another one comes from initial value conditions that I kind of deliberately stopped putting in the equations for V and for W. So what we need to show is that there are two things, actually. First is that this psi maps this holder space into itself for some beta bigger than 0. But we also need to show that it's actually a contraction in this space. The second part is easy, and it happens basically by choosing T random, but is small enough so we can make such argument. So the first part is the trickier one. So to facilitate the argument, I would try to keep track of where everything is at each part of this this mapping side that we're using in terms of the holder or negative holder spaces. And the rightmost are going to be more regular than the leftmost because you have some, you have monotonicity in holder regularity, right? So the first thing that we do with that map is really exponentiate. And it turns out that you have a Holder function, the exponential of this Holder function within that in the same domain is also a Holder function. Okay, that part is easy. Then we want to know, then the next part is multiplying the equation, multiplying this exponential against one of those fields. And we would expect this to just be in the field of, or in the space of smaller regularity, right? If you have a function that is twice differentiable and a function that is 4 times differentiable, if you don't have any further knowledge, you expect that their product is going to be twice differentiable. But here we're multiplying a function by a distribution. So we need to have some extra care. There is the sense of multiplication of C-infinity functions for distributions, but those functions that we're assuming, they only have finite regularity to start with. But this is easy to do. There is the Young product theorem. And here I'm being very informal with how I state this theorem. It's basically, I can make sense of this product meaningfully, and meaningfully here is kind of carrying a lot of weight. It basically means that it extends the point-wise multiplication and that it's continuous in between those two spaces, as long as the sum of the two regularities is bigger than 0. So, so coming back to our map, as long as alpha plus beta is bigger than 0, we can make sense of both of those products. The product of this x gamma epsilon and this e to the gamma w epsilon, and the other one as well. So what we want to do now is to consider what is the regularity of this new operator here when you convolve against Q, our modified semigroup that we're just dealing with. And here is really where our results come into place. This is our new contribution to it, is showing that we do have a gain in regularity, and this gain in regularity comes from the fact, comes exactly, we gain 1 regularity, basically. So we gain 1 minus kappa for any kappa positive. So we're actually gaining regularity by, it's a Schauder estimate kind of setting in the Bezold spaces. So our map Xi, which I'm actually ignoring those pesky terms again, maps W epsilon to from C beta to some C1 plus alpha minus kappa. So it's mapping C beta into itself as long as 1 plus alpha minus kappa is bigger than beta, and also along the way we use the fact that alpha plus beta is positive. So this happens, we can do satisfy both assumptions as long as alpha is bigger than minus half. And because we estimated before what it was the optimal convergence for the fields x gamma epsilon, we actually know for which parameters gamma, for each gammas we can have such a convergence. And here it's useful to mention that, so if we could make sense and try to approach this further in for further values of gamma, but then we would depend on regularity structures or something fancier, maybe power approach via rough paths as well. But you can just use this Prato-Debush trick that we just used of splitting into the nice part and the bad part. You need to do some more iterations on this, basically. And also, I kind of forgot to say at the beginning, but as I mentioned, the exponential nonlinearity had already been studied in this in SPDs in the same the Prato-Debush regime. What is nice for us, it was really about getting some nonlinearity that allow us to do our analysis, at least for gamma small enough. So this is not the main contribution. Our main contribution is really on the Schauder estimates, which surprisingly hadn't been done for these fractional Laplacians before. Right. And then we can conclude the solution of the equation, define basically the solution of the equation by the limit of the sum of the two, which is going to belong to C alpha. right? Oh, sorry, not to C alpha, to C minus minus kappa, which is actually the regularity of the linear part. Yeah, so this is the least regular one, and this is the most regular one. So the sum of them is going to live in the space of the least regular one. And I just want to give a few words on the heuristics of such Schauder estimates. The idea, it's really comes from Harer's Schauder estimates in that he used in regularity structures, that it was basically the following. If you have the same group, so say for the Laplacian itself, this is a smooth function with exception of the origin, and it has some nice self-similarity properties as well. So what he does there is to write this function, the semigroup, as a series of smooth functions, both in space and in time, and they're all perfectly smooth. Sorry, I will wrap up in like 2 words. But the thing is, for us, these are not, they're not smooth in time as t goes to 0, because the non-locality actually makes so the derivatives in time are not smooth. So we have to do a further expansion on each of those terms and split them into infinitely many, now not just with support bounded away from the origin, but also bounded away from the line t equals to 0. So that's kind of the spirit of the proof. So thank you very much. I think that was it.
Very good. So now we start with the questions from the jury. So the tradition is to order the jury by distance, Euclidean distance, but to the
But where to now?
the place. But now this is nowadays this is no longer a useful way to order people. So maybe we just go with an arbitrary order. So in my screen there is Francesco, then Jean-Christophe, then Claudio, then Patrícia. So let's go in that order.
Okay,
so
from the first one. Okay, first thanks Leandro for the very nice and clear presentation, and for the results that you told us. Okay, I have a couple of comments and questions. Let me start with just some very general ones. Since you have been talking about the fractional Laplacian, you have been mainly focused on the symmetric version of it.
Yes.
I was wondering about possible extension to non-symmetric, say asymmetric fractional Laplacian. And it's a bit annoying that for alpha equal 1, in the Cauchy case, this is a bit annoying due to centering issues. But I was just wondering whether if you could deal with it, or there are some technical complications that you.
So the result is really boils down to the difference between the characteristic functions. We try to match the characteristic functions of the lattice random walk against the continuous time one. If you're trying to do a result of the same sort for non-symmetric ones, you could compare either the green function or the local CLTs to their non-symmetrical counterparts, as long as you could match the two characteristic functions. I believe that the results work perfectly the same way. But then you actually, the problem with this so far is really constructing the examples, because given if you give, depending on which random walk you give me, I will be able to expand or not the characteristic function. There's a lot of heavy lifting happening in this proposition, which was, these article was supposed to be my first article and ended up being my last one precisely because of this. It's a bit tricky of actually estimating those characteristic functions. So if you're able to do that, all the results work basically the same, and you can recover green function estimates same way as well, but provided that you can expand the characteristic function. So this is annoying. We thought about doing this in some sense of based on a coupling, but it just turns out that when you're trying to quantify those problems on stable distributions, you really have to, there is some way you really will need to get technical, right? There is no clear gray single parameter that you can classify everything. This was our best attempt to really just transfer everything to the characteristic function, and suppose that the characteristic function is nice. So you could just do a version of what we mean by admissible by saying is equal to the characteristic function of bunch of non-symmetric random walks plus an error of order 2 plus alpha. And then we could do the same.
Okay, and the same could apply, I mean, perhaps it's easier, on the other hand, for the last part of your talk, that is the SPD, the sign. In that case, could you replace the fractional Laplacian by an asymmetric version, or
I'm not sure, actually. I didn't think about that. That would depend, again, we kind of use, well, particularly the half Laplacian is nice because everything is very explicitly it's still the Cauchy. We do believe that the results hold if you can just prove this. Basically, what we use is that you have some bounds on the derivatives in time as t goes to 0. And, well, in the half Laplacian, this is one line, you just make the computation. If I remember correctly, everything also holds for arbitrary powers of the Laplacian in between 0 and 2, also because of the characteristic function. I never did this for non-symmetric. I think it holds. It's the simple guess, but I'm not entirely sure.
Okay, yeah, I also think, I mean, there should be no problem in that part in allowing asymmetry. Now going slightly, more into technical stuff about your Schauder estimate. So you were describing the problems in applying Martin Heirer's approach, so that you had to tweak to get to the result. I have a comment and a question. First, very roughly speaking, somehow in its most basic version, the Schauder estimate in the Martin Heirer's languages is that when you take the convolution between a distribution with Hölder regularity alpha and a kernel which is say beta regularizing, then you get a distribution which is alpha plus beta Hölder. And now the meaning of beta regularizing means, roughly speaking, that it decays close to the diagonal as the inverse distance to dimension d minus beta. Okay? So in your example, d is equal to 2 because you are time and space, and so beta is equal to 1 because the kernel of the somehow Cauchy walk decays just like 1 over time, so there is exponent 1. So I mean, it's heuristically clear that you should improve by 1. My question is, so which part of the assumptions of Heirer fails? Is the derivative with respect to the space component, to the time component?
It's actually working on this. We kind of took it for granted, and I don't think we were the first people to take it for granted. It was actually Claudio who first pointed out that this was a problem. I think we all assume that it's C infinity outside of the origin, and it is really the derivative that matches. You don't even at first. So part of the result of Heirer is to give meaning of the convolution. You have to make as a series of convolutions against smooth functions, but those functions in our case cannot be smooth either. So you first have to make sure that a definition for what is this convolution against those functions that are not smooth in time anymore.
Okay, and
so it's more technical at the end of the day.
Yeah, this I understand. But then a question: you say you get the improvement of the regularity by 1 minus kappa for arbitrary small kappa. You think that kappa is just an annoying technical some artifact that could be avoided, or you expect some logarithmic divergence? I mean, because if I had to translate just the statement, I would expect an increasing indeed exactly by 1. While here you have 1 minus kappa. It's just you.
But I think that. Well, I don't remember how the Schauder estimates work for the fractional, even in the case of the Laplacian in Bezout spaces. I think you still have this reminiscent minus kappa as well, right?
Because I think. Okay, I think for the Gaussian case there should be no minus kappa, but okay, I might be.
Because our constant does depend on kappa, and I'm sorry, I can't remember now. I think it explodes as kappa goes to 0.
Yeah, I guess that from your proof it should explode, but perhaps if you have a feeling that you are just making some rough estimates and in principle it should hold with kappa equals 0 or not. But,
I mean, in spirit, yes, but I can't affirm for sure.
Okay. Okay, then I have just a couple of more general comments. First is about always about this last part. When you have the convergence of the renormalized equation, W bar epsilon, and then you get the convergence, I was wondering whether you can single out explicitly which feature of the white noise we are using. I mean, the whole idea of this regularity structure and paracontrol calculus is somehow to split the analysis and the probability part. And now it's clear that from your viewpoint, you are interested in the convergence of the renormalized solution. So there is no, I mean, you don't have to separate the two parts. But still, I think it would be nice if one can just say, okay, I can prove the result, but the only feature I am using of the initial noise is not perhaps that it's really the whole feature of the white noise, but this and that feature need to converge, and then I will have the converge of the renormalized solution. So I like to give a more pathwise version of the convergence result. That would just a comment.
I see. The feature that we're really using is that by taking the half Laplacian and the white noise, we really have more covariance, right? So it's kind of sorry, I'm just listening to myself. We're really using more covariance.
Can you mute yourself, maybe?
Sorry?
Can you mute yourself? There's a bizarre echo from you.
Oh.
So here really using that with the white noise and the half Laplacian, the solution of the linear equation is really log covariant, right? So for this equation in particular, this is very important that it's log covariant. But if you're looking at alpha stable, for the alpha power of the fractional Laplacian, and you're using a noise with a covariance that decays with according to some polynomial, just so they balance out to get the linear solution to be logarithmic, I think you could do the same analysis. I don't know if this answers your question, but this is the main feature that we're using. It's just to obtain the log covariance. Because as I mentioned, we kind of started looking at that, expecting to see some other behavior, maybe study on long-term behavior. But we ended up stumbling into this part of the non-locality being interesting, leading to having to prove those Schauder estimates as well. So that's why we kind of stopped here in this project. But you could do for all the noises as well, as long as you can control the covariance in some way.
Okay, thanks. And just a very last comment on the first part. you mentioned the difficulty of working with the characteristic function development, and I perfectly see that point. And a comment I have is that when I worked on related problems more in the renewal theory framework, and in the case alpha less than 1 of infinite mean, so it's a bit different, somehow I had to struggle a lot, and I never managed to use characteristic functions. And it turns out that in some context, using real value, some real space arguments like smoothness property of the transition kernel itself, perhaps coupled to other estimates, could be a solution. I mean that if you want to look, I mean, there is this big jump phenomenon, so that the big jumps matter a lot. So perhaps the smoothness of the jump distribution, of the step distribution of the random walk for large space as an additional input to the characteristic function, or just could be a direction to get possible results. It's a very vague comment. I'm not saying don't have a precise.
The argument that we use, we kind of, at the end of the day, it boils down to showing how smooth quotient of smooth functions is, and it's kind of an awkward approach. Like, no, it's not very traditional, but I think our method will only get us this far. I don't think we can really improve the what we used, but it's not clear at all that this is the best that you can do, for instance, for a repair distribution. Maybe the error is smaller, actually, and this is one thing that we're trying to see. What exactly, it's clear for us that this is the best local CLT that you can get. You can actually produce examples just by convolving a P alpha with a P beta, and you can get anything getting close to this. But it's not clear for us how to improve the characteristic, the heat kernel. So we're trying to see what are good assumptions to put here.
Yeah. The direction was not to improve the results or the bounds, just to give easier assumptions to work with or to check. Because as you mentioned, checking characteristic function development can be tricky often. So, okay, thanks a lot.
Thank you.
Okay, so now it's Jean-Christophe's turn to
all right.
make his questions and comments.
Yeah, thank you very much. So yeah, first of all, thank you very much for the presentation, which I found very clear. Yeah, so maybe starting with the first part, in your class of admissible distributions, there is this set R alpha, or this regularity set. And you assume this set to be finite. Can you comment on this assumption? Why do you need that it's finite? Like, could we imagine a version where we like remassage the assumption a bit so that it would also include cases where the sum is kind of cannot be written in this form?
Oh, sorry. If it's not necessarily in this form, so we're also the case alpha. We can translate the same kind of assumptions for alpha up to 2, and perhaps having a regularity set. And this is precisely, it translates into fourth moment or something like that. Turns out that if you take alpha exactly equal to 2, instead of this sum, you're going to have theta squared log theta. And you can recover some form of local CLT there, but the error is only going to fall logarithmic. And we were not sure if this was actually an interesting result. Maybe I can share another.
But if for instance, I know that the phi theta is the first two terms, like 1 minus the thing to the alpha, and then I only know it's big O of theta squared, let's say. Can I still say something, or is this?
Oh, no, you can. This is. It turns out that as your results are going to get better as far as you get on this regular. if you get anything just to beta being strictly smaller than 2 plus alpha, that's fine. You can transfer the same results. It's not really dependent on that. What is clear for us is that actually improving anything above order 2 alpha doesn't help with local CLTs. But it still helps with green functions, because it turns out that in local CLTs, we're really comparing against the random walk, and in green functions or heat kernels, we're comparing against the Levy process. And there it's kind of nice to have more terms here. So the further you have on your expansion, the better chances you have on recovering anything that you want. But you could rephrase this with milder assumptions on just going up to alpha plus epsilon. And it basically, this next factor after alpha is what dictates your convergence rate.
Thanks. I had questions about the Schauder estimate also. So you said that this was not known prior to your work. So you mean it was not known in the negative regularity spaces? Because I suppose that in the positive regularity spaces,
positive it was known.
All right. I did not understand the comment about the kernel not being smooth. Isn't the kernel just t over x squared plus t squared, something like this?
Yes.
And then that you periodize?
Let me just share another.
If you have a tablet, that would be awesome. I know.
Right. So you have that. I don't know. Can you see it?
It's coming. Yes, that's great. Thank you very much.
No worries. So you have that the kernel for alpha equals to 1. This is just 1 over pi, if I remember correctly. T x squared t. Right? And if I remember correctly, if you differentiate 0 x 0, this is actually 1 over t squared, or 1 over x squared plus 1 or something like that, maybe plus 0. But the thing is that in Herrer's case, he really thinks of k tx with the exponential and divided by to the d. They think of a function is moved in the whole time space, even for t smaller than 0, right?
Oh.
And they actually use that. He actually uses that. So it turns out that
is that right? Like he doesn't want to use the kernel will be 0 for negative t.
Yes. So you just complete by 0 in the negative time. Doing that here, it's going to lead you to non-continuous derivatives in time. And this is a feature of non-locality, basically, because you will explode at any time because of the big jumps, right? And this happens for any power flow.
When I was reading your thesis, I was very confused by this point. I was like, but t over x squared plus t squared, this is smooth. Like
I know. It was actually really funny because the moment that Claudio told me that, and then I messaged Milton, and he was like, I can't believe it. Like, you must be lying or something. And I also, this just goes without saying, and we don't really check on this at times. And it's funny because these kind of equations are still studied in any dimension that people have even applied BPHZ. And I have talked even to Martin and to AJ, and they all believe that it's perfectly true. But it's some annoying work to make sense of every step. One of the future projects is really doing that for every alpha, every dimension, and really transporting this to regularity structures, because I think there is no way that this result is not true. But
we are mathematicians. We wrote proofs. Yes.
So it's kind of amusing, but it's really. It's a simple.
Okay, so now it finally clarifies this. Okay, thanks.
No worries.
Yeah, this caused a bit. Okay, no, this. Okay, I skip. So if you have to single out perhaps one key difficulty that was fundamental to your work on the divisible SandPile, what would that be?
There in the SandPile, it was really about making some good estimates of eigenvalues of fractional Laplacians on the torus and having a proper understanding on them. This was kind of the tricky part, and because, well, this perhaps is where it's less clear here that I use green functions, but it's basically, well, everyone, I think, uses at some point that green functions, even on the torus, you can write as sum of lambda k. And this is nice to compare against even on the continuous torus. So what we really needed to do was to have a good understanding of the eigenvalues depending on alpha and n. That was kind of the, how do I say that? That was basically trying to adapt the proof from Wioletta, Cipriani, Alessandra, and Rajat, but having to account those these eigenvalue estimates that boil down to some convergence rates of certain integrals. Okay. So it was more of a technical nature. And we do, again, expect this to hold out, not just for power laws, but for any distribution sufficiently nice. Maybe in the domain of attraction of a distribution would be enough, but maybe we need to ask admissible or whatever. We're not really sure.
I see. I had now a question which is kind of tangential or not really well into what you have worked on, but I think there is some relation. So it's somewhat related to the first part. Mm-hmm. So imagine I observe these a series of IID random variables with this alpha stable, like in the domain of abstraction of this alpha stable law. But I don't know what is alpha, and I'm a statistician, and I want to know what is alpha. Like, given that you have worked on thinking, quantitatively about, how these finite sums look like the limits, I was wondering if you would have some ideas about what would be perhaps a good procedure for estimating the exponent. I don't know if my question makes sense, and no, it's not super mainstream to your work, but.
Yeah, I don't know, actually. That's a good question, but I haven't really thought about how to do that. I would assume that there is something about it, but I'm not sure, actually.
I think the question I would really be happy to hear some insight about, but which maybe for later when you have more time to think about it. I think you could imagine several procedures to estimate the exponent, but maybe some are really bad and some are okay. And yeah, I'm wondering if we could sort out which is which. I think, yeah, at some point, I think I had read something about this. And yeah, you can imagine several procedures that, asymptotically will reveal to you what is alpha, but maybe some are really lousy and some are doing well in some sense. I don't know.
Sorry, I don't know if I fully understand. So you're talking about the case where you have your characteristic function and you have some expression that is not necessarily a sum.
You're just going to observe. Yeah. So maybe within the same class of admissible distribution that you use, you're observing a sample. But I'm just telling you that I picked okay, maybe with some better assumptions, but I tell you, maybe it's one of these admissible laws with some alpha. Maybe the exponents the constants kappa are also reasonable. Maybe the set is finite, and maybe there are at most 10 terms or something. Like things are not crazy. And I'm asking you, and I show you, I don't know, 1,000 samples of these random variables. Is there what's the best thing I can do to estimate alpha?
Well,
it's a bizarre question.
I haven't thought about this before, and might be completely wrong. But so the first term is all you need to talk about your limiting distribution, right? All the other terms don't really fall into it.
Sure.
So I think you could estimate like what is the max beta just by comparing. If you have several random walks, you could estimate the final one against the initial one. Sorry, to the limiting one, and try to see. I don't know. I have no idea.
What I mean is that if you only see a finite sample, you will not be sure about what is the exponent alpha. So you will want to have a quantitative bound, and maybe you will need to have the expansion in order to figure out which procedure is best. Right?
I thought that you were giving me this part, and you wanted to understand this part. No, so in that case, I have no idea.
No, you don't even know what is alpha. So because so the physicists they like these power tail behaviors, and they want to estimate these exponents, but in fact, as far as I understand, it's not super clear what's the decent procedure for estimating the exponent.
Yeah, but I have no idea, to be honest.
Well, okay, I mean, I told you it was a kind of a random question. So I saw in your conclusion that you were discussing, in the conclusion of the manuscript, I mean, discussing maybe some disordered versions of the sandpile model, or disordered versions of the these Gaussian field studies. Can you expand upon this?
Yes, of course. So this was something that we got excited about, and this is actually in one of my slides of what to do next. But basically, we note this is based on one of your articles, actually. In your book with Cusi and Armstrong. Basically, so suppose that you have. Well, you can do that either on the discrete setting or on the continuous setting. On the continuous setting, there is no analog for sandpiles, but you can just think of the field. Say, if you want to say what is the fractional Laplacian, the bi-Laplacian, you could say it's the solution of this equation. Laplacian, right? With mean 0, and the GFF you could define as being the field for which you have the covariance kernel is just the green function of this operator, right? So you can generalize Gaussian fields, and it turns out you can even use, there is your article, I forgot, with Gu, talking about generalized Gaussian free fields that you do in terms of the covariance of the noise, and you can even put on these terms. We managed to show that this field, the solution of this field, does converge to the bi-Laplacian up to a constant, and same thing for the Gaussian free field. The Gaussian free field, you only recover convergence in distribution, but for the bi-Laplacian, you can get convergence in probability, or even almost surely, depending on some extra assumptions. And the idea is basically using that. Well, if you have the bi-Laplacian on some field, on some domain, if you have the Laplacian on some domain, you know that there is a basis of attraction, orthonormal basis for it, right? Then you can just try to solve these equations. X lambda k by k, and mean 0 equal to 0 outside on the boundary. Turns out, and that's just very convenient for us, that the green function for this operator, nabla a epsilon nabla, is equal to the original orthonormal basis times this pseudo orthonormal basis that we just defined here, and lambda k for the same lambda case. So you can actually transfer your results to convergence in any gain of regularity in your results of equations such as, instead of, I think, if I remember correctly, you assume L2 error, you assume F in W1 alpha, W2, I don't remember, F epsilon, and you can do this in any, in Sobolev spaces in general, basically. You can kind of use this fact and use that to understand the convergence rates for this particular choice of operators, together with some interpolation techniques to understand norm W1 plus alpha P that I think shows up on your book, you can actually estimate this in terms of the eigenvalues and recover convergence in a field that it's very reminiscent of, you recover conversing one less regularity than that F leaves in, right? Because even in the case that F is W10, you only get convergence without second order correctors. You only have convergence in L2, and we kind of recover an analogy here. So, and we can do the same thing on the discrete level. The thing is that this is very convenient, and we wanted to take this to the heat equation, but unfortunately it doesn't quite work there. We're trying to think of new approaches to do heat equation, because it would be nice to do homogenization for SPDs in general, right? But for now, we can at least do for elliptic fields, like fields solving an elliptic kind of equation.
Okay, well, thanks a lot for all the answers, and I think I'm done with my questions.
Thank you.
Okay, so next one in line is Claudio. So,
right.
Claudio, please go ahead.
Well, thank you, Leandro, for congratulations for this very nice presentation and all the results. Congratulations to your advisors as well. I have only a few questions. So regarding the first part of your thesis, so what are the applications you have in mind for these?
Oh, okay. So the thing that we really wanted to do with this, well, there's several models of like stochastic growth models that are very well understood in the local scenario, right? So this is actually, I think, is also on the extra slide. But for the first model that we wanted to understand is the IDLA, for which you have given up, basically you start with one particle at the origin, and then you put another particle at the origin and let it move until it leaves this cluster, like it leaves the origin. Then you kill this particle and add this to the cluster. And you keep going with this. This is a Markov chain. And well, in dimension one, this is a kind of a boring model, because it's just the Gambler's ruin problem, right? You can compute everything explicitly, but in any dimension, you can actually, you do understand, it's easy to prove that this converges to a disk, like to the heat ball of this process. What we want to explore is IDLA, for instance, for non-local random walks. I haven't even seen these results for finite range, but it would be particularly nice to look for long range, see what are the speeds of how fast it grows. Also,
why do you need central limit theorem for that?
Sorry?
Why do you need local central limit theorem for that?
Oh, so part of the proof is using, so how it actually works is that those proofs of those stochastic growth problems, first you need some understanding of heating times, expectations of heating times. And then you translate this into green functions estimates. And then you transfer this to local central limit theorems. And this is like, there's a lot of references to Lawler and Limmick book, which came exactly from this, like people using applications of green functions to understand some field that had an underlying random walk. So it turns out that this is one important step to understand such models, but there is one other thing that we need, is to look at the distribution of the first step outside of a rectangle, like outside of a ball, outside of an interval. This is easy to solve in the simple random walk case, but it's not very clear how to do in our case. It's done in the stable case as well, like in the continuum, but there they take advantage of some integral equations that are very explicit and you can really compute things. In our case, in ZD, you don't really have such explicit formulas for first heating times of a set or things like that. And we think that this is an important step towards being able to understand it. such random walks. So, and also one thing that I didn't have time to explore is, okay, maybe we start with this repaired random walk, and that's nice, but maybe you can even recover results for the original random walk, because as I said, what we are really interested in is not necessarily the green function, but into heating times. But you have a good coupling between the repaired random walk and this the non-repaired one, right? They only differ by something that scales like the Brownian motion. So maybe you can kind of control that as well. So that is our expectation. But the clear objective for us is to analyze modules such as IDLA, SandPile starting with mass 1 at the origin and like non-local as well in ZD. This has been done, the local version for it, but this kind of heat ball or shaped theorem kind of results, which we expect to be very different in dimension 1 with long range.
Okay, so one place in which I use local central limit theorems in statistical mechanics is in the proof of the equivalence of ensembles, in which you want to compare the canonical measure with the grand canonical measure. And then you need local central limit. And this, together with this zero-range process in which you have accumulation of particles, condensation they call, so that might be a possible application for these type of results, so that you have the stationary states which are given by product measures which are in the domain of attraction of a stable law, and there you want to prove these type of equivalence of ensembles, and what you prove might be useful in this context. Then what I've seen recently also are large deviations in which you have these type of distributions in which you have different types of regimes. So if you look at different regions of your space, then you get different decays, exponential decays, which, well, yeah, as I said, depends on the region at which you looked at. So that might be also...
I think the theory of, I might be wrong, I actually didn't even refer to it here, but it's somewhat well understood, the large deviations for those, and I don't think you really need to put in the format of admissible random walks. But if I remember correctly, there are, even for random walks in the domain of attraction of a stable distribution, large deviations are kind of well understood. I might be wrong.
Yeah, but what's interesting in these are these different types of regimes that appear, and that might depend on these sets R which you defined. So this is regarding to the first part, and then on the second part, I would like to know. Well, do you know more about these fields related to these fractional Gaussian fields, level sets? Well, you computed the covariance, right? So I would like to know if there are known results about these fields.
Oh, those fields are fairly well studied. I think results are, there are certain, basically the bigger the alpha, or like the gamma in our case, larger is the dimension in which becomes log covariant or things like that. But there is a certain relationship between this parameter gamma and critical dimensions, and people can actually transport a lot of results between dimensions by changing this alpha. There is a study in terms of maximums of those fields. I think ever since there was a beautiful review in this topic by, I forgot the four mathematicians that did that, but they kind of popularized those fields, and people have been studying quite a lot about them since. And I think there's a fairly good amount of information about it. I'm sure that there is some, certainly there is information that you would expect to be well known, but it's not yet. But those fields, it was Scott Sheffield, but there's other three co-authors, and those are well understood, I would say.
Okay. Well, thank you. These were my. Thank you to all.
Okay, so now let's pass the word to Patrícia. Patrícia,
here
you
I
there?
am. Yeah. Do you see me? You hear me?
Yeah.
Good. So first of all, let me thank Leandro for this very, very nice presentation. It was really clear, and I think you really presented very nicely. And I also want to congratulate the advisors, so Milton and Wioletta and Claudio. I think I should also thank to you because the third part of the thesis is with you. So I have some general comments, but not very much because we are already a bit late. But Leandro, this study that you do for the eigenvalues of the Laplacian, the fractional Laplacian on the torus, could you say something? Do you know something, for example, for the regional fractional Laplacian? So imagine that now you are...
I remember that we talked about this before, and later I remember this. It actually, I remember that there was a problem in the same regime as you did. It was for alpha equal to 1, right? Exactly. We actually faced this in the very beginning, and for some reason, this was really annoying for us as well, because I think that you basically break some symmetries of the plane, and because the regional fractional Laplacian, it's, I don't know how you define it. Is it in a box or is it in a...
Yes, you integrate, for example, in the interval 0, 1. So in my case, it would be the 0, 1, but you can define it in any region, any finite.
Are you defining on any dimension or just in dimension 1?
Dimension 1.
Okay. I think in dimension 1 it can actually be done kind of the same way, but I had a lot of... I might be wrong on that, but I remember seeing particular problems with this for larger dimensions because those fractional Laplacians for finite n, you lose some symmetries of the plane. You can't rotate it, and that's basically why fractional Laplacians don't... they are not commutative for finite n. And I remember we talked, I think, 2 years ago, and then later, like one of the first days trying to give meaning to these models, it was a problem with the fractional to the regional fractional Laplacian, that it was exactly at alpha equals to 1 as well. I don't remember what exactly was it, but just the convergence wasn't fast enough for us.
Okay.
But I think that maybe for dimension 1 there is hope.
Okay. So I see many applications on these in all these two first chapters that you studied about so for example, to study this extrusion process when you have long jumps and in contact with these reservoirs, for which you should get, well, you get in the hydrodynamic equation, this fractional heat equation with this regional fractional Laplacian. But anyway, I have now a curiosity. Because so your thesis is based on these 3 papers, right? Okay, 25, 26, and 27, the references. But so recently you are doing other things now. So I would like to know what is your future directions.
Okay. So that's
can you comment a bit?
I pull out the extra slide.
Yes, you talked about an extra slide. I wanted to see.
Oh, sorry. Okay. It's coming. Well. Yeah. So the first thing is this part of stochastic homogenization that we actually I forgot to mention as well. We actually started trying to do sand piles on percolation cluster, but there is some proper complications there. Even the sand pile, well, in the torus, studying the sand pile or studying the fractional field are basically the same thing. In the percolation cluster, there are some fundamental differences because the cluster messes up a bit with it. So this is one of the things that we want to pass to. We just finished the case of uniformly elliptic case, both in the continuous and in discrete setting, studying those fractional limits of as you homogenize those equations. So we want to apply the local CLT for IDLA in 1 dimension. This is certainly something we want to find applications for this, really show that this technique is powerful as we expect. Then this is a project that has recently started with Alexandre Staufer. I have started talking a bit, looking more into abelian particle systems like activated random walk and stochastic sand piles, which are related to the things that we worked on the thesis, not necessarily in for long range, but even a finite range is very interesting, or nearest neighbors. So this is something that I'm starting now. But for the last part of the thesis is really, well, we use a very specific choice here on this last part, using a half Laplacian and one dimension case. We do expect this to hold for other dimensions and other powers of the Laplacian. And irregularity structures, I think this is slightly more painful to do, but I honestly expect to hold the same. And what I think it's nice about our proof is that as soon as it's done, I think you can basically copy and paste in Harry's work, and you don't have to worry again about its use. It plugs it nicely. It's basic, which would be good for us. Of course, if you want to prove BPHZ and all the renormalization things, you might have to put more work into it, again, because those derivatives in time can make your life annoying. And finally, this is something that we really didn't have time to explore, but working in the exponential nonlinearity has been studied also by Garbin in the Prato-Debush regime, but it would be nice to look at the regularity structure level, because I have mentioned a few times, but BPHZ renormalization is basically, well, when Harry first made his paper, like there was several bits that you still have to put out a massive effort to analyze each equation. And then I remember listening in a conference, people referring to as the Old Testament of SPDs and the New Testament being like a sequence of papers that came after, like by analyzing each of those parts, looking at the regularity structures, how to renormalize the regularity structures at an abstract level, how to renormalize the kernels. And one of those parts is well understood. The BPHZ renormalization deals very well with a certain range of graphs, that is the language that they put. But basically, this exponential nonlinearity that we're taking into account, because it doesn't have finite moments of all orders, it kind of breaks some of their proofs as well. So it's also interesting to just see what happens there as we try to raise the value of gamma. This is also something that I'm interested in. And like there is several other questions that we raised during the PhD. I'm going to stay with Wioletta for a postdoc. And we're thinking of looking at the dynamics of the sand pile and other problems related as well. This is just a non-exhaustive list of things that I'm curious to do in the future.
Thank you, Leandro, so much. So I stop here. I will not ask you more questions. I think it's a lot. Congratulations again.
Thank you.
Okay, so now it's time for Wioletta to give her comments on Leandro's.
And Dirk?
Oh no, Dirk is gone.
Oh, was a substitute. So if one guy didn't show up, then Dirk was.
Okay. Yes. So I'm okay. It's my word. Yeah. So congratulations, Leandro, for a very nice talk. Extremely nice and intuitive introduction to all the nice things that you have been working on. Just one comment to Jean-Christophe's question. So actually, so there is a lot of theory about estimating these parameters alpha. So this is done in extreme value statistics. So they are basically the whole, so the whole effort is in estimating these tails. And so there's people like Mikos, Taku, Den Haan, etc., who has been done a lot of work on that. So there is a lot of literature on that. So maybe.
Okay. So thanks for. I didn't know. Maybe you could inform me more after we're done, because I'd be curious to hear more about it.
Yes. No problem. So is it okay if I read the little laudatio?
Yeah, of course.
So I have a picture.
Oh my God.
Another picture now. I was thinking how much.
Can you show it again? I didn't have time to. Yeah.
So my daughter recently graduated from elementary school, and they showed the picture when she was 4 when they started, and picture, So I was thinking, okay, let's do a picture when he started and after the period. So okay, so I just brief, I will read it out. I'm sorry for my Portuguese. Congratulação, Leandro. Van harte gefeliciteerd. Dear Dr. Chiarini Medeiros, dear Leandro, it is my great pleasure to be one of the first ones to congratulate you on your great achievement. I remember getting an email from Arnold von Enter asking if we have a PhD positions in Delft, because a brilliant student of Leandro Chiarini is looking for a position in the Netherlands. After some negotiation at the TU Delft and your successful application at IMPA, we managed to create this joint PhD project together with Milton called Scaling Limits in Sandpiles. The plan was that you spend some months in the second half of the first year in the Netherlands and the last circa 1.5 years here, and the complement of this time in Brazil. When you arrived in April 2017 in Delft, you have immediately found your place in the group. You participated in the PhD seminars, social gatherings, and were taken under the wings by some very enthusiastic PhD candidates from Delft, Bart and Jasper. I thought you would complain about the weather, the food, the people, that you cannot wear flip-flops, but you always stayed very polite and accepted your fate in Europe.
I use flip-flops the same way.
We started to work immediately on our first paper. The idea was to generalize the scaling limit results for the odometer of a divisible sandpile for the long-range case. So after I roughly explained you the main steps of the proof, you immediately went to work and produced beautiful estimates for controlling the discrete fractional Laplacian and its eigenvalues. You worked very hard, and I was very impressed by your level of technical skills, maturity, and intuition, which was already present at the early stage of your career. Within a few months, we wrote together with Milton our first paper about constructing fractional Gaussian fields from long-range divisible sandpiles on the torus. The results include a complete characterization of limiting fields of the odometer function and the determination of the order of expected maximum of the discrete fractional Gaussian field. As a surprising side result, we could even produce a GFF as a limiting field of the odometer. And finally, we got after many revisions, we got the paper accepted as SVA this year. Unfortunately, our paths had to part for some time, and you returned to Brazil, leaving me some papers, a suitcase, a box with a pillow to keep until your return in late 2019. In Brazil, you worked with Claudio Landim on a one-dimensional non-local singular SPD, where you studied well-posedness for long-range SPD, counterpart of the SPD which appears in the context of Gaussian multiplicative chaos problems. This result is very impressive study and non-trivial in the context of non-local singular SPDs. Now, we were trying to explore some further directions, like looking at divisible sandpiles in random environments, like percolation clusters, stochastic homogenization of the GFF and Laplacian fields, etc. And as a side project, we started to look at LCAT estimates for long-range 1D random walks with Milton, and using a cute repairing trick, I would call this, we were able to obtain optimal convergence rates. Moreover, we could obtain some explicit expansion of the potential kernel in the recurrent regime. Now, the last period was very tough for you. You had to finish your thesis under the pandemic, having had COVID yourself. Luckily, you could spend some period of time in the UK with Hannah, so you were not alone. You did not have the opportunity to travel a lot due to the circumstances, but fortunately now you will have the chance to catch up with that in your new position. We continue to work online, and I always enjoyed best the discussions we had using the 3 blackboards in the library or my nice blackboard in the office at the university. Thank you for the extremely nice time that we have spent together for the discussions. Under difficult circumstances, you obtained beautiful results in different directions, worked with different people, continued to be curious and motivated, and develop yourself both mathematically and professionally, made new friends on Stack Exchange, and still had time to teach me about Bitbucket and young adult language. You have an exciting journey ahead of you in your personal and professional life, I wish you that your dreams come true and you achieve your professional goals for many, 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 many new joint projects to come. Congratulations.
Thank you. Wow.
Okay, so okay, I should try to add something about Leandro, but I think Wioletta already said almost everything. So I will be very brief. So it's so Leandro has been probably the easiest PhD student I ever supervised. So I really feel like I was his advisor for like 2 or 3 months, and that was it. Because we started to work in January 2017 at IMPA. So I told Leandro, you know what, there is this alpha stable laws and these CLTs, and people don't really like to how to make it converge faster. So we should fix that. And then, well, we were working with Leandro, and quickly he managed to do this repairing procedure, that was kind of vaguely under the carpet at that time. And then I told him, well, now you have to go and solve your problems, because there's a whole world of long-range problems that people don't know how to solve, because basically they don't know how to get nice estimates, right? Everything it's only qualitative, and now that you know how to do it quantitative, well, go ahead, and that's it. Okay, so after that, you see, that Leandro went to the Netherlands, solved problems with Wioletta, came back to IMPA, solved problems with Claudio, and now he's really mature and researcher, really to go on its own, and I'm really happy for that. So, well, it's been really a pleasure to be your advisor, and that's it, no? So now, so the program is that Leandro has to leave the room, so we have a deliberation between us, and then we call him back when the deliberation is over.
Okay. Well, I'll see you then.
See you later.
The committee has decided to grant you your PhD degree. So congratulations! Now you are officially a doctor in mathematics.
Yay. Thank you very much, everyone. Thanks. Honestly, thank everyone for the help and the comments. I have many directions to look at now.
Yeah.
Right. I will probably, I try to make a little simulation of what IMPA's coffee room is like, and I made one of those gather towns. So I'll give you the link, and if you want to join for a bit, feel free to. Otherwise, don't worry. But thank you, everyone.
Thank you.
Okay. You're welcome.